So, today we will talk about the free energy from a different perspective. In the previous topic, we have been talking about free energy in terms of difference between delta H, that is the change in enthalpy, and T delta S, that is the temperature multiplied by change in entropy. But sometimes it is not the most easiest of way to calculate delta G, that is the actual free energy. It's a very tedious thing to really make the raw data of the values of delta G, because delta H as well as the entropy itself is a very dynamic and vague term. So, it is not easy, especially in the physiological environment, in the body all sorts of reaction are occurring. It is not easy that you calculate actual delta G value, and on the basis of it you can know the predictability of a chemical reaction. So, then we have to introduce another term, that is the standard delta G. The standard Gibbs free energy. The standard Gibbs free energy is the actually the Gibbs free energy in standard conditions, that is the conditions which is actually at room temperature and 1 molar concentration. This is represented by this expression, as you can see, delta G is equal to delta G naught plus R, where R is the constant and T is the absolute temperature, and ln stand for log, natural log, while B and A represents the concentration of B the product and A the reactant. So, in this way we can now relate the free energy with the concentrations of the product and reactants, because in the physiological system you are all the time dealing with the concentrations. Once you know about the concentration of reactant products, it is much easier than to calculate the value of delta G or delta G naught. Also, you should know that at the equilibrium constant of reactions is equal to the ratio of the concentration of product and reactants. And as I have already shown you in the previous expression, where delta G and delta G naught are related with each other through this ratio of concentration. You should also keep in mind here that when you are at equilibrium, when a system is equilibrium in our, for instance, in our body, then the concentration of reactant and product is equal. That is why it is a equilibrium, and as a result the value of delta G is equal to 0. So, taking these things in consideration, taking the value of K equilibrium here into this context, and keeping in mind that delta G is equal to 0 at equilibrium concentrations, the expression for the standard free energy will be this one, and this is a very important expression. Here, if you know the value of K equilibrium, and of course you know about the body temperature is always constant, you can predict the reaction whether it will be forward or reverse, because delta G naught value will tell you about it. So, this equation in that way is very, very useful. Now, you do not have to depend upon the actual free energy. Only by knowing the standard free energy values, you can easily calculate the value of delta G naught, and from that you can predict the direction of the reaction. For instance, if the K equilibrium is equal to 1, that is delta G naught is equal to 0, the reaction will already be at equilibrium. If K equilibrium is greater than 1, that is delta G value is smaller than 0, it is negative, the reaction will be moving in the forward direction. It will be, that is, more and more products will be formed, that we say the reaction is favorable. If however K equilibrium is smaller than 1, the reaction will not move in the forward direction, it will move in the reverse direction, because the value of delta G is delta G naught actually is positive. In this way, by simply calculating the values of delta G naught, you can predict whether or not a reaction will occur spontaneously, whether it will go in the right direction, that is the forward direction, that is the formation of the product will take place, or whether it will move in the reverse direction, or whether the reaction is at equilibrium. So, if I want to show you it graphically, so that you can understand it a little bit more, keep in mind that you should know what graphs are, you should learn to understand when a graph is shown to you. So, if K equilibrium is greater than 1, let us say this is A, this is the reactant, and the reaction start from here and it goes to the transition stage, the free energy is increasing and increasing, and it is going down, down and down until you get the B, the product. So, that the final state, that is, in the final stage you get energy level which is much lower, that is the delta G is negative. So, that is why the reaction will move in the forward direction, that is why A to B will be favorable. Opposite to this is if K equilibrium is smaller than 1. If it is smaller than 1, what will happen, that you will see the reaction moving in the reverse direction, not in the forward direction, but in the reverse direction. So, you do not see the products being formed in a forward direction, but now you have seen that reactants will be formed rather than the products, because the final stage energy level is much higher than the initial stage, that is the delta G is positive, as it is shown here, and here it is negative. So, you can see here that the standard free energy, how it helps us to the value of K equilibrium which we get from the expression of standard free energy, how it tells us about the how to help us to calculate that whether or not, or to predict whether or not reaction will occur in forward or reverse direction. Another very important property of standard free energy is that it is additive property, that you can sum up different standard free energies to really calculate the final energy level, and how it will help you to predict whether or not a reaction will take place. For instance, it may happen that a metabolic pathway consists of 7 or 8 reactions, and out of this some are unfavorable, some are favorable. So, what would happen? It may happen that you can think that the metabolic pathway will not take place because some of the reactions are unfavorable, but because it is an additive property, the standard free energy, what is here more important is that what is the final state of the standard free energy, and that final state, if it is negative, that is, if sum of all the standard free energies of all the reactions is negative, it will be a favorable reaction. So, this is an example you can see here, that when glucose phosphate is converted into a fructose 6 phosphate, we have positive delta G value, but otherwise we have negative delta G value when glucose is converted into glucose 6 phosphate. When we sum up both, the final delta G naught value is in minus, that makes the reaction to take. So, things to remember: you should know what is meant by actual and standard free energy. You know about the concentrations of the reactant product, how they are important, how they are related with the standard free energies, and equilibrium constant also. How we can use the equilibrium constant for the prediction of a reaction. and what actually is meant by and what are the benefits of the additive properties of free energy or standard free energy more. Little bit of food of thought, food for your brain. Why we use standard free energy at all? Why not we use the actual free energy? Why delta G is at equilibrium, a zero at equilibrium? Why it is zero when we reach to equilibrium? What is the reason behind it? What are the benefits of the additive properties of standard free energy?